but it will not be for everyone. Okay. If this is a function f of x, let's just say, and we're looking at it from A to B, and let's say you rotate it around, say, the x-axis, then you're going to get a shape that looks something like this for my particular curve. All right, if you want to find the surface area, that's how much, like, say, paint it would take to paint the outside of this thing. Or if you were putting a sheet of aluminum to make that shape, how much aluminum would you take? That's the surface area, okay? So to find the surface area, first of all, you would need, we're going to do it like everything else. We slice it into little bitty pieces and we add them all up together. But the idea is that you would have to find the circumference of this shape. To find the circumference of this circle, it's going to be a circle when I slice it. Circumference is 2 pi times the radius. But if I wanted to find the surface area of this thing, I would have to take that circumference and I would have to multiply it times the length of this curve. So the surface area would be 2 pi times the radius times the length of the curve. And we talked about the arc length formula. This is the arc length. The arc length formula I gave you if you have a function f of x. The arc length formula was the integral from A to B of the square root of 1 plus f prime of x squared dx. We had that arc length formula. So the idea here is if you slice this in a bunch of little slices and you look at the surface area of each little slice and then you add them all together, then you're going to have an integral. So the surface area for these shapes is going to be the integral from A to B, 2 pi times the radius times the square root of 1 plus f prime of x squared dx. The radius of this shape, in this particular shape, this line right here is the radius. Because if you slice there, you're going to get a circle. The axis is the center of your circle, and the radius is the distance from the center of the circle to the edge. Or if your function is a function in terms of y, if you have x is equal to g of y, if your function is in terms of y, then the surface area formula would be going from C to D on your y-axis. It would still be 2 pi times your radius times 1 plus g prime of y squared dy. Now, you can rotate these surface things, these functions, around either the x-axis or the y-axis. It doesn't matter whether you rotate it around the x-axis or the y-axis, the formula is still the same. But if you're rotating something around, let's just say this is my function, if I'm rotating it around the y-axis, my shape is something like this. The radius in this case is going to be that length. What was that? Nope. Nope. You still have this arc length. The formula is exactly the same. Yes.
One question I do have.
Yes.
On the radius, it's an arc, we can call it. You have to go up and change.
It's changing.
Right, but how do you calculate for that?
Okay.
Is what I
All right. In this particular case, you're right. The radius is changing. It's different. This looks like it's bigger than it is here. This length, this radius looks like it's smaller than it's here. So you count for the radius. The radius is determined by where you are on this curve. This radius is sliced, the way I slice this one, is sliced in the y direction. It's parallel to the y-axis. So, when you come down here, if you're in terms of x, you need to make sure that your radius, which is y, is written in terms of x. I'll show you. It sounds more confusing than it is. Making sense?
I get what you're saying, because it's parallel with it, so it's going to be a slice towards
It's
the
slice in the y. It's slice in the y direction into the x-axis, but it's in the y direction. Now on this one right here, when you're rotating it this way, this radius is sliced in the x direction. So this radius here is x. So if you're using this formula, then your radius would be in terms of x up here to go with the x's. If you're using this formula, you have to write your radius in terms of y. So that's how you take care of the different radius lengths, if you will.
Okay, but the reason why the question came out because you had dx, dy, I want to make sure there's
Yes.
something there that's throw me way out of whack.
It might. You've just got to make sure everything coordinates. For instance, if you've got dx, then you better have a function of x here, you better have this in terms of x, and these two things right here better be with respect to the x-axis. If your formula is in dy, if you've got dy here, then this better be in terms of y, this better be in terms of y, and these better be limits on your y-axis. So I would advise you to sketch some sort of picture, draw your line where your radius is, and then decide whether you need it in terms of x or in terms of y. All right, so let me give you some examples. All right, problem number 7. Find the exact area of the surface found by rotating the curve about the x-axis. This curve is y equal to x to the third. And it tells me my x's are ranging from 0 to 2. And I think I said this is number 7, and they want me to rotate it about the x-axis. Every bit of that's important. All right, the curve, y equal x to the third. If you don't know what it looks like, put it in your calculator, but it's going to be y is equal to x to the third, comes up like something like that. But we only need the piece of it from 0 to 2. So I need the piece from here to, let's say, here. So from x is 0 to x is 2. That's the piece that I need to look at. That's the piece that I'm going to rotate around the x-axis. So you take it and you rotate it, which gives you a shape something like this. Now we'll have to excuse my drawings, but it's going to look something like this. Okay. Where is your radius? If you're slicing this into different little circles, the radius is right here. My radius is y because I sliced it parallel to my y-axis. Okay? Now to set up your surface area integral, they gave me my limits of integration were from 0 to 2. So I would use 0 to 2. That is on my x-axis, so that, oops, I don't know why I wrote 0 to 0. 0 to 2. These, everything better be in terms of x, because this is x, these are x's, this is a dx. So right now it looks like that's the decision I've made. So I need 2 pi, and I need something for my radius. What am I going to put for my radius? My radius is y. But what is y equal to? I've got to write it in terms of x. What is it equal to? It's equal to x to the third. They told me it was x to the third. So my radius is x to the third square root of 1 plus. This is where you do your arc length formula. You need y prime, which is 3x squared. So I need 3x squared dx. This gives you your surface area. They want an exact value. So let me see if I can put it in here really quick. 2 pi times x to the third times square root. Okay, I got 145 square roots of 145 minus 1 times pi, all divided by 27. That is the surface area. If I got a decimal approximation for that, that would tell me about how much paint to buy, how much I would have to cover, how much surface area I had to cover. Yes?
Quick way to think of y prime is going to be n times whatever variable you have, and n minus 1 quick equation with 7.
On this particular one, there's just...
particular one.
Yes, on this
That's
particular
just a quick way to look at it. It's just helpful.
Yes, yes, yes. All right, that's okay. All right, let me just write down your question so I can make sure I answer it correctly. You're saying we have the same thing, but we're rotating it around the y-axis. All right, let's look at that one. We're going to look at the same problem. It's a great question. All right, so we have the same problem. Everything's given the same, except we're rotating it around the y-axis instead of the x-axis. All right, so draw your picture. My graph is not changing. I'm still looking where x is from 0 to 2 because that's where they gave it to me. But I'm rotating it around the y-axis, so this time it's going like so, and it would be going like that, sort of, with a lopsided top. Yes?
This creates limits to -2 and positive.
Why? Why? No. Not yet. I'm not doing anything. I'm graphing my information, and I'm going to label my radius. Here's my radius. My radius is parallel to my x-axis, so it's x. Everything up here is in terms of x. My limits of integration are in terms of x. This function is in terms of x. All I changed was where I rotated it, but it doesn't change what my surface area formula is. Surface area is still the integral from 0 to 2 dx. 2 pi times my radius. What did we say my radius was? We said it was x. Well, I've got x's here, so my radius is just x. The arc length part does not change because everything's in terms of x, so 1 plus 3y squared squared. Whoops, sorry. I don't know why I put y. 3x squared squared dx. These limits of integration have to do with x. This radius is at x. This is in terms of x. This is dx. So it doesn't matter whether you rotate on the x-axis or y-axis. What really matters is how you represent the radius, what you've got. Now, if you wanted to go through all the trouble of changing all this and put all y's in here, yes, you can do that. But to me, that was a lot of wasted effort when all you had to do was just pay attention to what you wrote right here. That's a great question. Okay.
So you just have to take this to what you're initially given as the reason axis or axis you're rotating around. So you'll know which one will right here today is in terms of the x one more.
Yes. And sometimes you may have to change something up here. You may have to change your limits of integration. If what they gave you is not working for you, change your limits of integration or rewrite your function. But you'll know when that happens, I think. All right, let's look at another one. Oops. All right, let's look at this one, number 14. X is equal to 1 plus 2y squared. y goes from 1 to 2. And this one is still in the same section. They still want it rotated about your x-axis. Okay. All right, this function, this is probably some kind of parabola type shape. So if I graph it, I guess I really don't know what it's going to look like, but I think it's going to do something like this maybe. My y is ranging from 1 to 2. These are on my y-axis. I don't really even have to really know what this function looks like in order to sketch a picture. Okay? If you want to look it up, you can. Look at it, you can. And this is probably not right. It's probably a square root. It's probably going the other direction. Yeah. You could, but it's really not necessary. What you need to know is, if you rotate it about the x-axis, the way I drew my picture, which is probably totally wrong, this is going to be my shape. This is my function x equal to 1 plus 2y squared. I need my radius. There's where you slice it. There's your radius because you rotated about the x-axis. My radius is parallel to which axis? It's the y-axis. So when I set up my integral for surface area, integral from 1 to 2, these have to do with y, so I'm going to go ahead and stick a dy out here because everything's got to be related to a y. And I need 2 pi times my radius. Well, I said my radius was y, so I'm going to put y times the square root of 1 plus, I need x prime for this. X prime is 4y, so I need 4y squared dy. Everything in this problem is related to y. So this goes in your calculator and you get out the surface area. And if you, I don't know if your question is this, well, what if you rotated about the y-axis? Well, all right, what would happen if I took that same picture, which probably isn't right, and I rotated it around the y-axis? This is then my radius. Yeah, how would I write my radius now? Nope. I can't have an x. Be more than that. 1 plus 2y squared. Right, it would be the integral from 1 to 2. 2 pi times my radius, which this time is in the x direction, so it would be 1 plus 2y squared, that's my radius, times the square root of 1 plus 4y squared dy. This is, again, this is another problem. This is not, I just don't want you to, in your notes, to think that we said that this is going to give you the same thing as this. This is rotated about the x-axis. This was the problem given. This is a what if. What if. Okay. Should I do one that is rotated around the y-axis from the get-go? All right, let's look at one more then. I'm going to look at number 18. All right, I'll have these notes up here if you want to take a picture of them. Number 18, y is equal to 1/4 x squared minus 1/2 natural log of x. Put that over 2. And my x's are ranging from 1 to 2, and this one is rotated about the y-axis. Okay, again, I do not really know what this graph looks like. I'll just stick something out here, but I know I'm worried about my x from 1 to 2 because it says x goes from 1 to 2. I'm going to pretend like my graph looks like that. If I rotate it around the y-axis, and I have this kind of shape for me, for my pretend graph. My radius is what? All right, my radius is x. All right, so when I start to set up my integral for my surface area, if I use the limits from 1 to 2, what am I writing all of this rest of the stuff in terms of? X, because that's x, these are x. I need dx out here. Even though it's around the y-axis, I'm using x's. So I need 2 pi times my radius, which is x, times the square root of 1 plus the derivative of this thing squared. So let me come over here and find y prime. Y prime 2 times 1/4, that looks like it's 1/2 x minus 1 over 2x. So I would have 1/2 x minus 1 over 2x, all of that squared dx. And I've got x's all the way across. That's in terms of x. This is x, x, and these are in terms of x. So that would be my surface area. Okay, question. Yeah.
Can the calculator kind of crunch this, or just don't?
Yeah, I'm not doing that by hand. If I do it by hand, I'm looking at in the back for a table of integrals. But yeah, I'm not going there.
No, I'm thinking calculators should have a problem crunching
Yes,
these. Okay.
yes. Come test time on the part where you can use your calculator, I am looking for your integral to be set up correctly. In fact, sometimes I may just ask you to set up the integral for me. I may not even ask you to calculate it. I may be asking you to set this up, in which case I'm looking for notation. If you forget your dx, you lose points. If you don't put your integral, if you don't put your limits of integration, you lose points.
Put the improper radius.
Oh, definitely. If you put the improper radius, you probably lose most of it, because that's part of the problem. You know, but I'm going to be looking for you to set this up. Using the calculator to spit out the answer is secondary to something like this right now. Okay? Or anything else on this surface area or area of the surface of revolution? You got it? Just looking at it? Deep thought. Deep, deep. Okay. Fixing to shift gears. All right, this is section 8.2 right here. I'm going to start, and I may get partially through 8.3 today. But 8.3, the part that I want to do right now, is, I guess, the easier part of section 8.3. There are actually two more applications of using integrals. And the application that I want to look at right now is finding the center of mass of what's called alumina, which is a flat plate. And it may have an irregular shape. It may be something like this. For sake, let me just draw this right here. If I had this flat thing right here, and I wanted to take that and I wanted to balance it on the end of this pencil. Suppose that were a sheet of metal and I wanted, not going to balance on my pencil, but pretend like it would. If I wanted to balance it on something like that, where is the exact point that I could put that pencil so that that shape right there would balance?
Not easily discernible without calculating.
Exactly. you could make a guess, and you may think, oh, well, maybe it's somewhere up in here, but I have no clue. But whatever that point is, that's what we're going to be finding, the place where we could balance that thing. And it is called X bar, Y bar. They call it the center of mass for these lamina shapes. X bar, Y bar, and they have formulas. So to find X bar, it's 1 over the area of the shape multiplied times the integral from A to B of x times your function f of x dx. If you calculate this integral, assuming this were your f of x, okay, then that would give you your x coordinate. To find the y coordinate, it's 1 over a times the integral from a to b of 1/2 your function squared dx. Okay, it's a formula. It's an integral. I'll work an example like that in a minute. Now, if your shape is bounded by two curves, suppose you've got a curve up here, which is your f of x curve, and maybe you've got a curve down here, which is your g of x curve. And the shape that you want to balance is something like that. The formula changes slightly because now you've got two curves that are bounding your space. So to find the x bar and the y bar here, the x bar is still 1 over the area, the integral from a to b, and we'll say this is point A and this is point B, the integral from a to b of x times f of x minus g of x dx. You have to subtract your function. And your y bar is 1 over a, the area, integral from a to b of 1/2 f of x squared. Let's see, we write like this. Minus g of x squared dx. All right, there are your two formulas. You can look at them while we work the problems, because I'll probably have to look at them too. Which means this is probably one of the formulas that you'll get to write down. Make sure y'all got it written. Yeah.
Are we on the section where it says multiple centers of mass?
Yeah. And in your...
So when we pick back up on another day, we don't finish that?
If I don't finish today, I'll pick back up on Tuesday, but it'll still all be on your test Thursday.
Right. No,
Yeah.
I know we left also today.
Yeah. And this is problems 10 through 12 on your homework, I believe. So you should be able to do, after today, you should be able to do problems 10, 11, and 12 on 8.3 homework. At least. I may start the rest of it. But y'all got this written down? Okay. All right, I'm going to put my formulas up there. All right, problem 26 is a good one to look at, I guess. Problem 26 in your book says sketch the region bounded by the curve. So sketch. Visually estimate the location of the centroid. Just make a guess and then find the exact coordinates. And my function is y is equal to the square root of x bounded by y equals 0 and by x equals 4. So before you can do anything, you need to sketch this. So you need to sketch y is equal to the square root of x. Let's see, square root of 1 is 1, square root of 4 is 2. That's 2. It's going to go something like this. I stopped at 4 because it said x is equal to 4. I'm going out here till x is equal 4. Which I'll get to this point. And then the other bound is y equal to 0. So I've got this curve, this line, and I need y is equal to 0. That's the other side of this shape. Which line is y equal to 0? The x-axis or the y-axis? The x-axis. This is the line where y's are all 0. So this is my shape that I want to find the center of mass. Okay, so make sure you know your boundaries. Now they are asking me to make a guess as to where I think this thing is going to balance. Oh, I have no absolute clue, but I'm guessing I would try somewhere around there maybe. I don't know. Just make a guess. You guess. Your guess is be as good as mine. But if you were to cut it out, try to put it on a pencil, where do you think you'd put that pencil to balance it? Okay? All right, first thing you need for your formula is the area of that shape. This is a Cal 2 problem, I think. Or Cal 1. Cal 1. Cal 2. The area under the curve. Cal 2. The area under the curve is an integral. So to find the area of this shape, I'm integrating. Where am I going to integrate to get the area under this curve? I need that. I'm going from 0 to 4. And my curve is the square root of x dx. So that, you just calculate that to get the area, the integral of I got 16 over 3. Okay, keep looking at your formulas. All right, this is what I'm looking at. I've got to have the area. That's why I needed it, because my x bar is 1 divided by the area, and then this integral. So for my x bar, I need 1 over this, which is just the reciprocal of this. So this is 3 over 16 times the integral from 0 to 4. My formula says I multiply x times my f of x. What is my f of x? Square root of x dx. So this is 3/16 times the integral from 0 to 4. That's x to the 1 plus 1 x to the 3/2 dx. You put it in your calculator if you want to. And I got this to be 12 over 5. Yes. That's the first coordinate of my ordered pair. Now you've got to find y bar, but you've already got the area, so you're still using, 3 over 16. Integral from 0 to 4. The formula for this one is 1/2 times your function squared. So it's 1/2 times x squared, that means times the square root of x squared. So this is actually, is it 3 over 32, the integral from 0 to 4 x dx. If I multiply 1/2 times 3/16, square root of that's x. You ought to be able to integrate this one by hand, but if you want to save time, and I'm going to do that right now because I'm going to save time. Oops. Probably do it quicker if you did it by hand. I got 3/4 for this one. All of these were easy integrals, and you should be able to do these by hand. This gives you an ordered pair, 12/5 and 3/4. And if we actually went back over here and looked at 12/5 and 3/4, 12/5 is about 2 1/5, and then 3/4 would probably be, so it looks like I missed it. Looks like it would be closer to that point right there. Yes.
We don't have to put a bar or whatever during the order pair of the number.
No.
I'm just making sure.
No. It's just a number.
Okay.
But if they say find x bar and y bar, that's what they want, is an ordered pair. Because it is an ordered pair.
Okay, I just want to make sure the number doesn't have a
No.
bar over there.
No. No. Okay, finding the area is the Cal 2 problem. Okay, the rest of it's the Cal 3. All right, let's look at one. Y'all, any more questions about this one? All right, let's look at one like number 29, where it's bounded by 2 curves, and see if we can figure out what to do with that one. The 2 curves are y is equal to x squared and x is equal to y squared. Okay, I'm thinking to have to graph these, so I'm going to solve this one for y, so I can graph it. Y is equal to plus or minus the square root of x.
Was it minus very important in this instance?
Yes, it's always important. If you get out of the habit of doing that, it's going to cost you when you get later stuff. All right, so y is equal to x squared. And you may find you don't need it when it comes all said and done, but you need to sketch your graphs anyway. And the square root of x, the positive square root of x goes up there, the negative square root of x comes down here. This one is y is equal to x squared. This one is x equals to y squared. The part that I'm concerned about is this little bitty part right here. So this part to this part. So I'm going to take that and blow it up over here. You need to know these points of intersection. I just happen to know them. Do you know how to know? Do you know where? This is 0. I know. I'll give you that if you know that. Do you know where they intersect right there? 1. If you don't know it, you've got to find it. So they are going to intersect at the point 1, 1. So you've got the top curve, which is this one, and I set it the way that I drew it. This was the, sorry, in terms of y. This was the positive square root of x. This was the positive square root down here. This was the negative square root. And then this part of the curve was the function y is equal to x squared. And I need to know those 2 limits of integration. I mean, because I'm going to use it for limits of integration, I need to know where they intersect. If you don't know, you set the 2 equations equal to each other and solve it. Okay. This is my shape. And I'm guessing, if I were balancing this thing, I'm guessing I'd be right there, somewhere in there. Looks like it. But I got to find it. So, for my formula, I have to find the area between these 2 curves. That is also a Cal 2 problem. To find the area between the 2 curves. Do you remember how to do that? like Cal 2 is a prereq for this class. Okay. The area between the two curves, you subtract. Top minus bottom. So to find the area, I'm going to integrate from 0 to 1. The top curve, that's why I labeled them. The top curve is the square root of x minus the bottom curve, which was x squared dx. Integral, let's see. X minus x squared. I got 1/3. Okay. All right. Remember, this part is you've had this before. You've done it before. Okay. That's the area. Now, to find your x bar and your y bar, you just again substitute in the formula. Remember, it changed a little bit, so look at the one that changed. The area is 1 over this, which makes that 3. The integral from 0 to 1. X times the square root of x minus x squared dx. So I'm just following that second formula that I gave you. Oh, times 3. So I got 9 over 20. And then y bar is 3 times the integral from 0 to 1. 1/2. Have to look at my formula. My f of x squared. So I have the square root of x squared minus the other function squared dx. Be careful that you read the formula correctly. That's the most common mistake I see. Square this function, square this function, and subtract them. So when I put that in, I got 9 over 20 also, which makes perfect sense to me. Yeah, because it was very symmetric, this and this. So the ordered pair that represents the center or the centroid is 9/20, 9/20.
Pretty close to what we have right there.
Yeah, that's probably, yeah, it is actually, isn't it? That's a guess. That was a lucky guess. All right, centroid of a region. Question. Okay, is there a question about anything that I've talked about so far?
Is there any news or dollars on there and stuff
In the calculator? Don't forget to tell your calculator to multiply. It's not too smart. I'm not sure if it knows.
Well, I was just thinking something simple, something like overrule.
That's what I was looking at right here. If I forget to put multiplication. Yep. If I take, oh, it's not gonna do it. Sorry. You can't see my screen. All right, this one enters differently than the ones that you just did. This should be respect to x from 0 to 1. All right. I don't know if you can see right here. You see where I have x, and then I have parentheses, square root of x. This was doing, which problem? This one. this one right here. If you just type it in straight across and hit enter, it's going to tell me I have invalid implied multiplication. It's not as smart as we are. If I write X right next to that bracket, it does not know to multiply. So a common mistake would be to forget to do that. You have to go back and you have to put the dot right there. So I would have to go, I'd have to quit here and I'd have to go all the way back and make sure I put multiplication there and then hit enter, and then it'll figure it out for me. So if you get an implied multiplication error, you didn't put times something. So that's the most common thing that I can think of. And that happens, that's on yours or mine, the Inspire or this one. Oh, and if you type something in and your calculator just starts spinning and spinning and spinning and spinning and spinning, what do?
Reset.
You reset it. Because it will just keep going. And
if you forget off the parentheses while you're doing a midpoint rule, it'll go.
It'll go off on a tangent.
Yeah.
And no, and it's on this one too. This one, to reset this one, you can just take your batteries out of this one in the back. Trust me, it's going to happen. It's going to happen sometime during this class. It will happen that you will lock up your calculator by typing something in that it can't do. So find your reset button. Okay? Okay. I know. I hate that for you. Okay. I am going to get a very brief start into the next stuff because it is, if there's anything complicated, it's this section. Hydrostatic force and hydrostatic pressure. And you said you know what I'm talking about with hydrostatic force and hydrostatic pressure, sort of, because y'all kind of do that at work with your pipes or something? No.
That was me.
That was you. Somebody did, I know. What did you say now with hydrostatic? It's the force of a fluid on a
Cylinder.
on a cylinder or a wall or anything.
We have done this. I've done this in physics before. It's not, it cannot be fun.
Okay. We're probably going to do it in here a little bit different than you do in physics, but it does apply to real life things.
I was just saying, what I was telling you is that we have tank levels that have to stay at a certain level when we're filling containers. As the hydrostatic pressure, which is the level of the tank drops, the overall pressure changes, so it feels slower if you don't have, if you don't keep it that height. So we have flow switches and levels, and that way it knows that if it drops, it pump immediately kicks on and fills it back up.
Okay, so that's pressure. Okay. We're also going to talk about force, actually. And I don't know if you have much to do with hydrostatic force.
This was 8.2.
This is 8.3. The first part of 8.3. Okay. We are talking about hydrostatic, I'll just kind of show you my notes right here. Hydrostatic pressure and hydrostatic force is the pressure and force of liquid on a flat surface. All right, first of all, the hydrostatic force, we're thought to get all these letters that we use in here. First of all, the area of the shape is the letter A. They use the letter A. Fluid density. Or if you've got water, it's a different density than if you had gasoline, or then I don't know what you've got in your tank. What do y'all have in your tanks or whatever?
All different kinds of stuff. We deal with herbicides, pesticides, insecticides.
Okay, that would have a different density level than just pure water. So the density is this letter right here. I think it's a row. The depth of your fluid matters. That's just their letter D. Since we're talking about a surface, a flat lamina, we're looking at the mass of that shape, its density, area, and depth. Now, hydrostatic force is the fluid density times the area times the depth times the acceleration due to gravity. Yes.
Back up, what did you say, the M1 again?
I think I pulled it from the book. I was trying to use their same letters. Let me find it. They say mass is pressure times volume. This is theirs for mass. Okay. All right. This is hydrostatic force on a flat surface. It has to do with the area of the surface, the density of the liquid, the depth of the liquid, and gravity. If you are in meters, then the water density is 1,000 kilograms per cubic meter. That's a given. Know that. That doesn't change if it's pure water. However, if you are in United States, feet, inches, then the weight density includes gravity and the water density, and it is 62.5. Okay? Feet, inches, meters. All right. Hydrostatic pressure does not involve area of the shape at all. Pressure is only to do with the depth of water, acceleration due to gravity, and the density of the fluid. Where are we? There. Yes. P times. That rho times G. Yeah. It's the fluid density times gravity. By the way, what's the acceleration due to gravity in? 9.81. We use 9.8. They're using 9.8. Okay. That's acceleration due to gravity if you're in meters. All right. First of all, we're going to look at pressure on a flat surface that is submerged in water. The pressure is going to be the same over here as it is over here, and over here, and over here, if it's flat. But and the force is the same, no matter where you are on that shape, But if you take that flat surface and you put it like this, vertical, yeah, like a dam or a wall in an aquarium, then the pressure on this dam, if you think about a river or a lake, the pressure of the water on this dam is going to be different at the top of the water than it is at the bottom of that lake. So this type of surface is not as easy to calculate as one that is laying horizontal. Horizontal is a piece of cake. Vertical is going to involve integral. Horizontal just involves sticking numbers and multiplying them together. Okay, so it's the vertical ones that are going to give us the problem. So needless to say, those are the ones that we're going to really look at in depth. Which do you think? What do y'all think? Bottom. Bottom. Yeah, because you've got all the weight of the water above it, and it's all pushing like that. So that, yeah.
You ever been in the swimming pool where you go to the deep end and get pressure?
Exactly. If you're like just scuba diving or anything, the further you go down, the more pressure you get on your body.
I think the Hoover Dam is 1,000 pounds square inch at the bottom, like a big water.
I don't know, but I just know when you're calculating building that dam, you want to do something different at the bottom than you do at the top. What I'm thinking, or your dam's going to be like this, and all the water's going to come flying out. So it has a very practical application as far as building stuff that's like that. Okay, so I'm just going to start off with a very easy problem. Number 1, looking at an aquarium. An aquarium that is 5 feet long, 2 feet wide, and 3 feet tall. Is full of water. So let me see if I can finish drawing this sort of. Okay. I basically can't draw and talk at the same time, so. is my aquarium, more or less. And it is full of water. Okay, seems like it's full of water. They want us to find first the hydrostatic pressure on the bottom of the aquarium. All right. How much pressure is that water putting on the bottom of that aquarium? Well, the pressure is the density of the fluid times the depth of the water times the acceleration due to gravity. Since we are in feet, the pressure and the gravity are this 62.5. So you have 62.5. The pressure and the gravity are the 62.5. It scared you? Did your aquarium explode or something?
Yeah.
You filled it too full. All right, the depth of the water is 3 feet. So if you multiply that, is that 187.5 maybe? And I am bad about units. Mr. Rogers would kill me because I don't know units. That's the math brain over here, not the physics brain. Sorry.
I thought y'all said to do it times 9.8, or not?
No, the 62.5 includes the gravity.
Okay.
Because this is weight density. You only have to include the 9.8 when you're in meters, kilograms, whatever. Okay. So the pressure on the bottom is 187.5 whatevers. All right, part B. Find the hydrostatic force on the bottom. Well, the only difference between the pressure and the force is the area. So all we have to do, the area of the shape, okay? So all we have to do for this is multiply pressure times area. So that's 187.5 multiplied times the area of the bottom. Well, the area is 5 times 2, which is 10. So this is 1,875. Flat surfaces, piece of cake. What should I say? Horizontal surfaces, piece of cake. Okay, still with me? All right, part C. Find the hydrostatic force on one end of the aquarium. Well, one of the ends is one of these vertical pieces right here. So I'm going to take that vertical piece and I'm going to put it out here. This is 2 feet. This is 3 feet. It is full of water. And I need the force. Yeah. It would be a limit, but to cut straight to the chase, it's going to be an integral. Because if you do limits, is that what you meant, integral? Yeah. That's fine, yeah.
From 0 to 2, correct?
Okay, you're definitely on the right track. Because we've talked about this. This is the same thing as a little bitty dam, okay? A little bitty glass dam, because it's in an aquarium. Pressure at the bottom of that is greater than the pressure at the top. So you can't just multiply some numbers because the force is not going to be the same here, 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 and here. It's different everywhere. So what you're looking at is essentially a limit, which leads you to an integral. Okay, so what you have to do for every one of these problems, and I'm just going to go ahead and start with this one right here. Somewhere on this drawing, you have to put an XY coordinate system. So you can get everything with relations to X's and Y's and get limits of integration. So I guess we'll just put an XY coordinate system right here, which means that's the origin. Now you said I was going to integrate from 0 to 2. You mentioned that. I can do that. But that would be 0 to 2 on this axis because you need to go with the depth of the water. Okay. So you would need to go from 0 to 3. You've got to integrate, yeah, the depth of the water. Okay? We can decide with all these pictures, you can put your x-axis up here. If you'd rather have your x-axis going this way and your y-axis going this way, we are flexible. In fact, it sometimes works better that way. But for sake of right now, we can just leave this to be y, and this can be x if you want to. We'll leave it normal. All right, when we set up our integral to take into consideration the fact that all of these little pieces are going to be different, you're integrating along this axis. The depth of the water is 3, so you're integrating from 0 to 3. All right, what did we say we needed for force? We need the density of the fluid, which is going to be, it's in feet, 62.5. The depth of the water and the area. All right, I'm just looking at this formula right here. Is it always 3? Remember, you're looking at the pressure, excuse me, the force right there. Is the depth of the water 3 right there? No. You're looking at the pressure right there. Is the depth of the water 3 right there? The depth of the water is not 3 until we get right there. Well, actually, it's 0. It's how much water is above you. Okay, this is where you can look at, all right, if you are at 1, and I'll let that's not very symmetric, what you need to think about is how much water is above you. Okay, so if you let y be 1, if y is 1, how much water is above you there? 2. Then the water is 2. If y is 2, if you're integrating at 2, how deep is the water there? If you are integrating at 3, how deep is the water there? How much above you is what I meant. 0. How can I write, as y is changing, how can I write an expression to get a 2? If y is 1, how can I get a 2 somehow? Somebody had an idea a minute ago that was right. What'd you say? Subtract. You're essentially subtracting 3 minus y every time. 3 minus 1 gives me 2. 3 minus 2 gives me 1. 3 minus 3 gives me 0. So the depth of the water is 3 minus y. Then the area. But what they mean by area, they don't mean the area of the whole shape, because it's different at the bottom. We are slicing this into tiny little pieces. We are slicing this little piece right here, and we are looking at the area of that little piece. The area of this is this length times delta y, because this is with respect to y, this line. This length is 2 feet. So the area of this shape is essentially 2 feet times delta y, which is your dy. So the way I'm telling you to set this up, this is the area of your shape, this is the depth of the water, and this is your acceleration due to gravity and all that stuff. And if you calculate this, this gives you the force of the water on that end of the aquarium. Go ahead, Ab. Do you have a question?
I feel like there's an infinite amount of numbers that you can place in for y between 1 and 0.
There are.
0 and 3.
There are.
Well, then how? I guess it could only be accurate whenever they ask you at which depth between. Like you see, like you have like 3, 2, 1, 0. Like you have those listed out there. So would it be accurate just to assume that you would just only use those?
Now this, I took that into consideration right there. Why? Because no matter what y number I choose on here, that formula will give me the depth of the water. If I'm right here at 1.5, if 1.5 is going in there, 3 minus 1.5 is going to give me a depth of 1.5, or whatever it is. See, when I make this changes with every one of these little y values. When an integral does, it's doing this one and 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 this one, and add them all together. The integral is the limit of your real sum.
So you're doing one in one, another y2, another y3, another y0. and
I did
you're
this to
all
get that formula.
Right.
Yeah. That's all I use these, because these are nice, round, whole numbers, and I knew I could figure it out. So I wrote this down to help me get what I have to do. This is not a constant. It has to be an expression of some kind. Now, this is a constant because every time I slice it 2 feet. In this particular problem. Now, if this is a slanted line, it changes the situation altogether. Even that's not going to be a constant. Yeah, your hand's
I
up.
was going to say, can you say you pretty much flip the scale without what to say it? Like when you 3 minus y, say you're flipping the scale, it starts at 0 and goes up, but you really got,
Yeah.
if you're at 0, you've actually got 3.
I've got 3 feet, 3 feet of water. No, we got inches. No, we got
That's
feet.
feet. I'll only.
We haven't even clear.
That's what I'm
Okay.
saying, you pretty
Yeah.
much flip the scale, what you do by doing that.
Yeah. Now, the thing about this is I set my XY coordinate system up there. You might have set yours up differently. All right, so on this homework, that's one thing I forgot to tell you. On this homework, if you even start to look at it, some of the blanks on your homework are worth absolutely nothing. You could put stuff in there and it'll tell you it's right or wrong, but it doesn't matter. The points aren't going to count. They want you to set some of these problems up in a particular way. They want you to set them up the same way that they want to set them up. I go with the notion that you can set this up several different ways and get the right answer. I want you to go with how you see it. So I think on these problems we're dealing with force and pressure. If it's asking for an integral, that's not going to count towards your grade. What counts towards your grade is the answer. Even though I'm going to be looking at integrals from test time. I'm not sure if this is making any sense at all. And I thought I brought my homework with me, but I guess I did not. I wanted to show you the little blanks that don't matter. Because I don't set mine up the way they do all the time. All right, should I look at one more before I send you on your way, or do y'all want to just mull that over and we'll talk more about this on next week? If y'all have, let me see if I can set one. I'll try to do one that's not hard. All right, let me just do this one. This is problem 3. They've got this picture drawn. They've got this skinny little rectangle. This is 2 feet wide, 8 feet tall, and there's 3 feet of water above it. The water is up there.
Can you go ahead and add your X and Y coordinates on this or not?
You got to have an XY axis somewhere.
No,
Is that what you're saying?
Can you go ahead and do that step now?
Yeah. In fact, that's what I would do. But I'm just kind of waiting and seeing where y'all want to put your XY axis, because I don't.
At the bottom of the rectangle.
Y'all liked it at the bottom where we had it a minute ago, like down here with your origin here. Okay.
All we have to do is water all the way to the bottom of the rectangle.
Yes.
Do the correct section.
Yes, because this is submerged in water. I mean, it's all the way, and it's vertical in the water. It's 3 feet underwater. Need an XY axis. Do y'all want this to be, you want to set it up normal? You want this to be X and this to be Y? Sure, okay. We'll set it up that way. Now, you were only interested in the force, the pressure on this little thing right here. There's nothing up here to have pressure on it or force on that, okay? So we're just interested in this right here. So if you're setting up your integral, here is where you are integrating. So what are we integrating from? 0 to 8. This whole thing is 8. So we're going from 0 to 8 to get up here. All right, this is in feet. So you need the density of your water. And it says water. Yeah, it's plain water. So 62.5.
Would it be 11 minus y? You're having to count for the whole distance.
Okay. Yeah, I think it is. All right, so the next thing you have to do, make sure you're following the little kind of guide. The next thing you have to have is your depth of your water. And he said he thinks it's 11 minus y. So before we actually write it up in there, let's see if it is. All right, when you are down here at 0, at the bottom, how much water is above you? So when y is 0, pardon?
I guess it depends on the weather.
On the weather that day. Well, this is a pool of water. I put waves in mine, but yeah. All right, yeah. The water's 11 feet deep. If you are at, let's just say if you're up here at 3, how much water's above you if you're at 3? 8. So his formula, 11 minus y, works. All right, now what you have to do, you've got density, you've got depth of the water, now you need the area. Every time you slice here, you're slicing 2, it's like the other one. And the, right, dy, sorry. And the little, yeah, length and width is the dy. So that should give you the force. Express the force as an integral and evaluate it. This is the integral I would use, and if they ask you for this on WebAssign, this may or may not be what they want, which is why I said this isn't going to count for them on WebAssign, but the answer does. They don't set it up the same way I do. Now this is easy. Now if you'll look at all these pictures that we're going to talk about, these are going to be set up a little bit different. I mean the same, but not as straightforward, because when you try to get your area, exactly, your area is not going to be the same. Your area is not going to be the same. This one's only halfway submerged. So you know you're going to have to look at that. This is halfway submerged. So I will look more at these, but I wanted to give you a start on how to start thinking about this.